Hello everyone, this is our fourth and final section about block diagrams. Today what we're going to talk a little bit about is how to actually define the interfaces that interface to a block. So let's look at that right now. So here's an example of a block that we pulled from our previous design. This is the processing block. Notice it has the sensing to processing analog signal coming in. It has a code to processing code coming in. Power supply to processing DC power coming in, and it's outputting a processing to network data interface. So again, this is directly from the example we've seen in the previous block diagram videos. You'll also notice that I'm using the formatting that's required from our IEEE formatting guide for the course. So let's go ahead and look at the table. So here is the table of interfaces. So you'll notice that I've defined each of the interfaces by name as the row. I've listed their type, and then I've listed what I call specifics. So specifics are properties of each interface that can be tested. It's pretty important that you define these well because, for example, the processing block is talking to the sensing block. And both the person designing the sensing block and the person designing the processing block have to understand what they're designing to. If there's some ambiguity among the specifics or there's just some missing specifics, it's possible for the people doing the two different blocks to design different outputs or inputs than what's actually needed for each block to talk to each other. So that's why these specifics are important. There is a web-based tool for entering these. What's nice about that tool is it keeps track of when people make changes, and it notifies people when changes have been made. Arguably, if you met weekly and you met or even more frequently and your group discussed everything fully, you wouldn't need to have a tool to help keep you on track. But what we've seen from years of experience is that it's important to be able to have kind of a final version, or a version at least that your TAs have looked at, as well as each of you have looked at, and when changes are made by anyone, everyone that's going to be affected by those changes gets notified. So that's why we use the web-based tool. Anyways, back to this example. Let's look at this sensing to processing a signal. So V-range, the term V-range, this is implying the range of the expected voltages. So 0 to 5 volts is the range of what we would expect to come in. One thing to note is each of these kind of headings that we're using in specifics, they vary interface type to interface type, and they might not exist in every specific interface example. There might be things that are more important. Continuing on though with sensing and processing, we have the temperature is 0 volts at 0 degrees C and 5 volts at 40 degrees C with a 5% tolerance. This is pretty important to have a tolerance because there's no way you'll be able to accurately, precisely enough measure these voltages and these temperatures. So make sure you have a little bit of a wiggle room. 5% is what's expected. If you ever have more than 5% as a tolerance, you'll probably have to justify that with the grading TAs. Depth, 0 volts is 2 centimeters and 5 volts is approximately 1,500 centimeters or 15 meters. Which is significant, of course, but that's what's necessary for this particular application. Imax is 20 milliamps. Now this is an analog signal. Why do we list a maximum current? This essentially is indicating the output impedance of the system. So what this is saying is that the processing block, which is the one we're working on now, needs to be designed in such a way that when this interface is connected, it does not draw more than 20 milliamps. And that's something that you can test. Okay? If we were on the other side, the sensing block, you would need to design a sensor such that if the system that is connected to the processing block was to draw up to 20 milliamps, all of the other criteria would still be accurate. How does this play out? Well, for example, if you're going to measure temperature, you probably couldn't just use a thermistor and another resistor as a voltage divider, because that 20 milliamps of current draw from the center node would deflect the readings that you were getting. Additionally, you have frequency max, 100 hertz. This is more of an indication just to say, hey, how fast are things going to change? So we assume no more than about 100 hertz, which is going to be able to set the sampling rate of your processing block. Looking at the code processing code, that's a great interface name. We've decided it's going to be a C language. It's going to be downloaded via an Atmel Mark II programmer. The code size less than 16 kilobytes, going to configure UART and an ADC. This is pretty flexible, what goes inside of this section. Obviously, we've kind of committed ourselves to Atmel by this interface specific. That being said, these are changeable. So if we found something better, we could always change it. Power supply, processing DC power. So Vmax, 5.5 volts. This is the maximum voltage that will ever be seen on this line. The processing block is consuming this power. Therefore, it will be tested with 5.5 volts powering it, doing all of its tests, and Vminimum, 4.5 volts powering it, doing all of its other tests. So it has to work within that range. If we were doing the power supply block, the other side, when we were testing it, we would need to prove that the power was within this range. Back to the processing though. Peak current, 200 milliamps. So this block should never draw more than 200 milliamps at any time. I nominal, 50 milliamps. That means that this block should draw approximately 50 milliamps. Now, that being said, we probably should put a tolerance on this. So we'll add that in. Because 50 milliamps, that's too precise of a number. So let's give it a little bit of wiggle room. Processing to network data. So here's an example of some communication protocols. So for example, it's UART 8N1, 8 data bits, no parity, 1 stop bit. It's going to be 5 volt logic level, so 0 and 5 volts. It's going to transmit at 38.4 kilobits. And this is a little bit about the actual data being transmitted. Depth and temperature measurements transmitted as ASCII strings in the range of 0, notice the string, to 1023, notice the string. It's going to be transmitted most significant digit to least significant digit. I cannot tell you how many times I've seen people struggle with this. When you're communicating over a serial line or any communication line, there's a difference between sending an ASCII string that represents a number and just sending the number. It's pretty confusing for folks. So make sure it's identified whenever you're transmitting some data, and then make sure you account for it when you're writing your code. This format actually is pretty similar to what you might want to have right at the beginning of your document when you're writing your block descriptions at the end of ECE 441. All right, great. Good luck, and we'll see your block diagrams soon. Thanks.